All right, we're on the final section of Chapter 1. In this video, we're going through Section 1.7, which is on linear, compound, and absolute value inequalities. In this section, we're not talking about equations. The equals is replaced with an inequality, greater than, less than, greater than or equal to. How do we solve inequalities? You could absolutely have a circumstance where in real life or at your job or wherever, where you're trying to solve for an inequality, not an equality. And here it just gives an example. Emily wants to earn an A in her college algebra course and knows that the average of her tests and assignments must be at least 90, right? Must be at least. She has 5 test grades. She also has a score of 100 on her homework, which is weighted the same as a test grade. She needs to take the final exam, and the final is weighted 2 test grades. So what score does she need to get in the final exam so that her average grade is greater than or equal to 90, right? That's an inequality. A linear inequality it's the exact same thing as a linear equation, except instead of equals, you have an inequality sign. The solution set to a linear equation consists of a single element that can be represented by a point on the number line, right? The solution set to this, to x plus 4 is equal to 0, is just one number minus 4, a point. But the solution set to x plus 4 is greater than or equal to 0 is everything that's greater than or equal to minus 4 on the number line, right? The solution set is different. To solve a linear inequality in one variable, we use the following properties of inequality. Okay, so the properties of inequalities. If x is less than a, then a is greater than x. So you can flip an inequality, kind of like you flip an equation, but when you do that, you need to flip the sign, the inequality symbol, which makes sense, right? If you have 4 is greater than 3, and you want to write this with the 3 first, then just put 3, flip it, right? Okay, if A is less than B and B is less than C, then A is less than C. All right, so if 5 is less than 9 and 9 is less than what? 11, then 5 must be less than 11, right? Because if 5 is less than 9, then 5 is less than anything that 9 is less than, including 11, 10, 12, whatever. All right. Property 3, if A is less than B and C is less than D, then A plus C is less than B plus D. So think about what this is saying. It's important to understand these properties. We can use them to solve certain problems. This seems complicated. It's really, really simple. If I have, let's say minus 3 is less than 2. All right. Now, I'm going to add something to this minus 3 and something to this 2. Not necessarily the same thing. But all I know is that what I'm adding to this minus 3 is less than what I'm adding to 2. But starting off, as we can see, this is already less than this. Then 100% the result's going to be that what this results in on this side is going to be less than what this results in on this side. So let's say I'm going to add minus 3 plus 5. Okay, that's 2. All right. Now I'm going to add something to 2. But no matter what I add to 2, it's definitely going to be greater than 5. Something greater than 5. So it could be 6, 7, 8, 9. Well, okay, well that's going to be, if it's 6, it's going to be at the very least, it's going to be 6 if we're just talking about integers. At the very least, this is going to be 8 because I'm going to add no less than 6 to 2. So it's going to be 8, 9, 10. Well, no matter what, 2 is less than that. Okay? All right, if A is less than B, then A plus C is less than B plus C, and A minus C is less than B minus C. This is the property where you can add or subtract something to both sides of an equation, and the equation doesn't change. It's the same thing with an inequality. If you add or subtract the same number from both sides of an inequality, the inequality doesn't change. All right, here's where it gets a little bit different than a normal equation. If C is positive and you have A is less than B, this is your starting inequality, then AC is less than BC. So multiplying both sides by that positive number doesn't change the inequality, or dividing both sides by that positive number doesn't change the inequality. So that's just like a regular equation. But if C is negative, then if you multiply both sides, you have to flip the inequality. If you divide both sides, you have to flip the inequality. That's where it's a little bit different. You have to remember that. All right, and then this doesn't, if you have greater than or equal to, it's the exact same. These properties are exactly the same. Okay, and we're going to work examples where we solve equations and we have to use these properties. And here you can see they start with minus 6x plus 4 is less than 34. They subtract both sides by 4. The inequality doesn't change. Here they have minus 6 is less than 30. They divide both sides by minus 6, but they have to flip the inequality, right? And they get x is greater than minus 5. So the solution set to this inequality is any number that's greater than negative 5. Okay, a linear inequality containing fractions. We're going to work a bunch of examples, but it's very similar to a regular equation, except that negative, if you multiply or divide by a negative number on both sides, you have to flip the inequality. It's very similar to solving a regular equation. All right, compound linear inequalities. Compound inequalities are statements with two or more inequalities joined by the word and or the word or. For example, suppose that X represents the glucose level measured from a fasting blood sugar test. So the normal glucose range is given by X is greater than or equal to 70, this unit here, and X is less than or equal to, so between 70 and 100 inclusive. Abnormal is less than 70 or greater than 100. So, right, you could have the glucose level be too low or too high. So that's the idea. You could be solving for what values of an input, of whatever input, right? It doesn't have to be the glucose level. It could be, you could have some function with different inputs or one input or whatever that gives you the resulting glucose level. But you want to solve for what inputs is the resulting glucose level less than 70 or greater than 100. Right? That's the inequality you're trying to solve. That's a compound inequality. It's you have two or more inequalities joined by the word and or. Right? This is a or statement. And they give an and statement here. So you could be saying if it's normal, for what values of the input is the glucose level greater than 70 and less than 100, right? So to solve a compound inequality, first solve the individual inequalities by themselves, okay? Solve the individual inequalities by themselves. If two inequalities are joined by the word and, the solutions are the values of the variable that simultaneously satisfy each inequality. That is, we take the intersection of the individual solution sets. So the idea is you solve the inequalities individually by themselves, and then if it's an and, it's just how you view the solution set. You don't do anything different. Like if it's an or question, then you just interpret the result as an or, right? So if we come here, this or this, solve both, and what you get is X is greater than or equal to 7 or X is greater than 12. And so you just graph the solution, right? It's this. This is the solution. Anything less than or equal to 7, anything greater than 12. That's the solution. Okay, but let's say this was, for some reason, this was and. X is less than or equal to 7 and X is greater than 12. Well, there's no solution to that. That can never be true, right? So we're going to work a bunch of examples. You'll get the hang of this. All right, here's an and statement. They solve both. T is greater than minus 8 and T is greater than or equal to 2.5. So and that's just T is greater than or equal to 2.5, because if T is greater than or equal to 2.5, it satisfies this and it satisfies this. And see, that's it. Now, sometimes a compound inequality joined by the word and is written as a three-part inequality. So if you see a three-part inequality like this, sometimes you'll see inequalities like this. That's just an and compound inequality, right? So 5 is less than minus 2x plus 7, and minus 2x plus 7 is less than or equal to 11. So you can't do this with all and compound inequalities, but if they have the same term like this, then you can make it a compound with like it is here, like a three-part inequality, you see? And so to solve a three-part inequality, the goal is to isolate x in the middle region. And so what you do is, if you're going to add, like, let's say you want to get rid of this 7. So you subtract minus 7. You subtract it from all three parts. You subtract 7 here, subtract 7 here, subtract 7 here. If you're going to divide or multiply, you do the same idea. Now you're going to divide by minus 2, so you flip each symbol. All right. Now there's also absolute value inequalities. The absolute value of x is less than 3. What's the solution set to that? That's anything between minus 3 and 3. You plug any number between minus 3 and 3 into this equation, it satisfies the equation. Anything else, it doesn't. The absolute value of x is greater than 3. So it's anything that's less than minus 3 or anything that's greater than 3, right? You get the idea? And so with that logic in mind, we can come to here, the properties involving absolute value inequalities. So if you have a real number, k, that's greater than 0, so a positive real number, if you have the absolute value of u is less than k, then you solve this compound inequality. This is an and compound inequality, right? If you have the absolute value of, and this u is an expression, like it's not just this could have variables. The absolute value of u is greater than k, then that's this or inequality. And then the statements hold true for even if you have greater than or equal to, less than or equal to, it doesn't matter. Okay? And we're going to work a bunch of absolute value inequalities. Now, they give some special cases of absolute value inequalities, and we're going to work examples like this as well, but let's take a look. The absolute value of x plus 2 is less than minus 4. There's no solution to this, because no matter what we plug in, the absolute value is going to be greater than 0, right? Now, if we take the opposite of that, let's flip this. Well, no matter what we plug in, it's always going to be greater than or equal to minus 4. So the solution set is all real numbers. Okay, so here the absolute value of x minus 5 is less than or equal to 0. So this works because we have that equal. Well, there's only one solution to this, because the absolute value of x minus 5 can't be less than 0, no matter what, but it can be equal to 0, right? Now, if we come here, the absolute value of x minus 5 is greater than 0. Well, this is anything but when x is equal to 5 is going to satisfy this, right? Any negative number, any positive number, as long as x is not equal to 5, this equation is satisfied. Okay, applications of inequalities. So word problems with inequalities. This is really helpful to get a sense for where these come up in real life, where inequalities can come up in real life. So we're going to have a whole playlist where we work a bunch of word problems with inequalities. But here it gives that test score example, right? What do I need to get on my final exam so that my final average grade is greater than or equal to something? Here's another example. So suppose that a machine is calibrated to dispense 8 ounces of orange juice into a plastic bottle. Okay, so ideally it would dispense exactly 8 ounces with a measurement error of no more than 0.05 ounces. That's the measurement error. Let x represent the actual amount of orange juice poured into the bottle. Write an absolute value inequality that represents an interval in which to estimate x. Okay, so the measurement error is plus or minus 0.05 ounces, right? It's no more than this. So the actual amount poured into the bottle is going to be the absolute value of x minus 8. That's going to be less than or equal to 0.05, you see? And you solve that and you get what x is, the possible values for x. I don't know, that's not the best example. We'll work other examples. You'll get a better feel for situations where inequalities come up.